Hey everyone, it's Dr. Walker. This is video 54C on rotational motion. Let's start this video with a question. It says, which part of the turntable moves faster, the outer part where the ladybug sits or part near the orange center? So what do you think? Well, believe it or not, the answer is actually it depends. If you're thinking about motion the way we've talked about it up till now, which is linear motion, then the answer would have been the outer part. If you think about the ladybug, it has a linear velocity that is tangent to the circle. So over here it's moving in this direction, if it's over here near the front, it's moving to the left, etc. That's a linear velocity. So yes, it would have a faster linear velocity on the edge rather than towards the center. But in this chapter, we're talking about rotational motion, so we're going to look at motion circular, and we're going to use angles. So think about the angle through which the ladybug is rotating. So you start the ladybug here, and she's doing a full revolution. Well, that's an angle of 360 degrees. If the ladybug is over here, well, she's also doing that full 360 degrees in the same amount of time as if she's over there. So as far as angular motion and the angle that she rotates through per time, it's going to be the same no matter where she is. So the purpose of this question is to just give you an idea that we're going to look at motion differently. We're going to look at things rotating instead of moving in a straight line. An important thing that we'll see is that every point on a rotating object has the same angular motion, but it does not have the same linear motion. And we'll see this written again a few times, because that's a very important difference between rotational motion and linear motion. Let's start our description of rotational motion or angular motion. Let's start with angular position. Let's say we have a point on a wheel here, and it rotated from this reference line, which is usually the positive x-axis, all the way up to here. Well then, it went through a certain angle theta. And this theta is defined as S over R, where S is the arc length, and R is the radius of curvature. You can see it in this picture that the arc length is this curved line here. It represents the linear distance traveled from the original point to the final point, but you see that it's a curved line instead of a straight line, so it's an arc length. Divide that by the radius and you'll get theta. Theta is measured in radians. If you're not familiar with radians, let's refresh briefly. So the radian is a unit for angle. If you think about a circle, then a full revolution is 2 pi radians. Perhaps you remember the unit circle from high school. Let's see that our definition, theta equals S over R, let's see that it makes sense. Let's consider one complete revolution. S is the arc length. Well, if we have one complete revolution, the arc length would be the full circumference of the circle. Full circumference of a circle is 2 pi r. If we divide this by the radius r, we can see that the r's cancel and we get 2 pi. This is measured in radians. So this was just to see that this equation makes sense and just to see what a radian is equal to. So if you have 2 pi radians in one full revolution, then you know that every 90 degrees is pi over 2 radians. We can write down an important conversion factor. A lot of times in problems we're given the number of revolutions of an object. So one revolution is 2 pi radians, so we can write this as a conversion factor. 2 pi radians is also equal to 360 degrees, but we don't use that as frequently. Now we can talk about our kinematic quantities. Back in linear motion, we had delta x, we had v, and we had a. Displacement, velocity, and acceleration. That was for the linear motion. Well, now that we're talking about rotational motion, we're going to go through these same quantities, but they're going to have different names because they're going to represent rotational motion instead of linear motion. So the first quantity is the angular displacement, delta theta. It's going to be the final angle minus the initial angle. So if an object moved from point A to point B, it had an initial angle, it had a final angle, you subtract the two, that gives you that angular displacement right here, which is delta theta. So since theta is measured in radians, so is our angular displacement. So you can think of delta theta as the rotational equivalent of delta x. Now let's talk about angular speed. Angular speed, back in the linear quantity, was defined, if we look at the average speed, it was delta x, or average velocity, it was delta x over delta t. Well, now the average speed is going to be the angular displacement per time. How quickly we travel a certain angular displacement. Whoops. So if we want the angular speed, this is the instantaneous angular speed, but we usually just call it angular speed for short, then it's going to be the derivative of theta with respect to time. And we got this by just taking the limit as delta t approached 0, just as we did with the linear quantities. So angular speed is measured in radians per second because it's an angle per time, radians per second. Now we do have a convention of what is positive and what is negative. So in general, if we are rotating counterclockwise, that is considered a positive speed. If we're rotating clockwise, that is considered a negative speed. I actually had that as a note here and I forgot to show it. So the sign convention that we use is that an angle or speed is positive for counterclockwise motion, but negative for clockwise motion. Let's take a look at this question. Rashid and Sophia are riding on a merry-go-round that is spinning steadily. Sophia is twice as far from the axis as is Rashid. Sophia's angular speed is blank that of Rashid. Well, do you remember our ladybug example? We said that no matter where the object is on the rotating object, the angular speed is going to be the same for any point on that object. So the answer is it's going to be the same. So really pay attention to what is being asked. It specifically said angular speed this time. Let's look at our final variable, the angular acceleration. You'll see that it looks very similar to the linear analog. Average acceleration was delta v per time. Well, now it's delta omega per time. The change in angular speed per time. Right? If you're spinning this roulette here, well, you might not spin it at a constant speed, right? It might start slow and then speed up. So you can have some acceleration when an object is rotating. We can also define the instantaneous angular acceleration as the derivative of the angular speed per time. And the unit is radians per second squared. It used to be meters per second squared, right? Now it's radians per second squared. So the thing about this video here is that these quantities that we are seeing, they're the same as before, but now they're just corresponding to objects rotating instead of moving in a straight line. One more note is about the direction. We have said, well, if it's rotating counterclockwise, that's positive, clockwise, that's negative. However, technically, angular velocity is a vector, and it has to have a direction. And the way that we specify its direction is using this right-hand rule. What you do is you curl your fingers in the direction of the rotation. So in this case, this object here is rotating counterclockwise as viewed from above. So our fingers are rotating counterclockwise as viewed from above. You see that rotation of the fingers is the same as the rotation of this object here. Our thumb points in the direction of our angular velocity. So that means that technically angular velocity, its direction, is along the axis of rotation. And depending on which way the object is rotating, depends what the direction of omega is. But we're really not going to use this direction very much. We're just going to stick with the non-vector notation that we just talked about here. But I did want to be complete in my description of these quantities. The last thing for the acceleration, it is also a vector, but we're going to do acceleration just like we did before. If an object is speeding up, that means that the acceleration and the angular velocity are in the same direction. If an object is slowing down, then they're in opposite direction. So the angular acceleration also has a direction along the axis of rotation. But again, we're not going to use it much. I just wanted to be complete.